Sampling distributions. Suppose some retired dude sells fireworks over the 4th of July holiday and Christmas trees during the Christmas holiday. And let's suppose their average revenue is $18,000 a day with a standard deviation of 3,000 here, and then 10,000 a day with a standard deviation of 2,000. Now, this is a strange combination, fireworks and trees. Some people say that you can't see the forest for the trees, but maybe you can't see the forest because of the fireworks, okay, and what they do to the trees, but I don't know. At any rate, we have this right here, and remember what we can do if we take like one day here and one day here, and what's probably the sum exceeds 30,000, that's a joint distribution. Not unlike this puppy right here. This is saying that we would take 2 days at random, maybe one's a Monday, maybe one's a Friday or something like that, and just suppose that each day is normally distributed like that. Well, then we would say, oh, this is a joint distribution, so to find the mean of this joint distribution, you would add 18,000 plus 18,000, and you would get 30,000. And then remember that to find the standard deviation, we take the variances, which is the standard deviations squared, add them up to get the new variance, and then take the square root to get the new standard deviation. But don't forget, what we're talking about is, on average, what's the sum of two randomly selected days? And this is how they can fluctuate due to random chance. Standard deviation is random chance. How much fluctuation do we get? We might get one that's like 19,500 and another one that's 19,200. But how should the sums of those two scores be distributed? That way, that joint distribution. What if we took 9 days at random? Do you agree that this would be the joint distribution for 9 days added together? Okay, well now let's do this. Let's talk about what if instead we were going to take 9 days at random, but add them up and then divide by 9 to get a mean average. What's the mean average for those 9 days? Well, it should stay pretty close to this mean average. The mean for any 9 days grouped together might be a little bit above or a little bit below. And there's infinitely many combinations of 9 days that we could find. So we want to explore what happens if you add up, take a joint distribution of 9 of these days, add them up, and then divide by 9 to get a mean average. Well, now we're talking about F bar, the mean average for 9 days added up and divided by 9. What would the distribution of means be like? Well, they would be distributed normally, and then think about this. You'd add 9 of these together, but you'd divide by 9, so 9 of the 18,000s divided by 9 would take us back to 18,000. And what that's saying is just on average, the mean of 9 days would be 18,000, but it can fluctuate. You have a few days that are above average in revenue, they pull that mean average up. Now, the big question is, what happens to our standard deviation of these sample means? Well, again, you would add up all the variances for the 9 days, take the square root, and that would give you the standard deviation for 9 days. But if you were dividing by 9, that's the same as multiplying by 1/9, and if you remember linear transformations, when you multiply by a factor, you just take the standard deviation and multiply it by that factor. So basically, you'd be multiplying this by 1/9, which is equivalent to just dividing this by 9. So take the sum of all the variances and take the the square root to get the standard deviation for the sum of 9 days. But then you know that you're going to be dividing those 9 days by 9 to get the mean average. So your standard deviation for sample means of size 9 would be that divided by 9. Well, now let's play that out. If you have 9 of these guys added together, then under the radical sign, you're going to have 9 of those 3,000 squared variances, all divided by 9. Because we're dealing with the sample means, so we got to divide it by 9. Well then, radical 9 times this, radical 9 is worth 3. So you're really going to get radical 3 times the square root of 3,000 squared, all divided by 9. And then, okay, so, radical 9 times that. And the square root of 9 is 3, so this is going to become 3 times the square root of 3,000 squared is just 3,000. And then this is going to get divided by 9. And 3 divided by 9, that's really 1/3. So what you're going to end up with is, very important, this is what's going to happen. When you take sample means, you're going to take your initial standard deviation of 3,000 and divide it, not by the sample size, but these guys cancel, and you're left with the square root of the sample size, which is 3. So we're going to find that the standard deviation of sample means is equal to the original standard deviation divided by the square root of the sample size. In this case, the square root of the sample size is 3, so our standard deviation would be 1,000. So, if we were to do this, let's take a random selection of 9 days of fireworks sales and find the probability that the mean exceeds 20,000. Well, if we were only talking about 1 day at a time, find the probability that 1 day's revenue would exceed 20,000, we'd be going to this distribution. Remember, the original distribution, the standard deviation for x, was 3,000. So if we went from 18,000 and we went up 3,000, 3,000 again, and another 3,000, then this is the distribution 1 day at a time. But we're not talking about selecting 1 day. We're going to select 9 days and add them up and find the probability that the mean exceeds 20,000. So think about this. We're likely to get a day down here, maybe a day really close to the mean. Maybe 1 day we get sales of 18,800, something like that. We get a day up here, 1 score at a time here, 1 revenue here, maybe 1 low one, 1 big one, and a couple more in the middle. But we're going to add up those 9 scores and then divide by 9 to get a mean average. Those mean averages will tend to balance out and stay really close to the overall mean of $18,000, because any group of 9 scores, that mean average will fluctuate due to chance above the 18,000. So enter the sampling distribution of means, this puppy right here. This describes how the sample means will be distributed if you took samples of size 9. So this is what we're talking about. The mean of those 9 days would still be centered at 18,000, but the standard deviation of the means would be the original standard deviation divided by the square root of the sample size. So it would be the original standard deviation of 3,000 a day. That's how much chance fluctuation there is 1 day at a time. But when we add 9 scores together and divide by 9 to get a mean, you're not going to get as much fluctuation, just logically, if you think about it. And so we take the original standard deviation and divide it by the square root of the sample size. Square root of the sample size is 3. 3,000 divided by 3 is 1,000. So the standard deviation of the means is only going to be 1,000. That's why you go over 1, 2, 3 standard deviations and you get to about the most extreme mean average you would expect from any 9 randomly selected days, being up at 21,000. So again, going back to our question here, what's probably that the mean exceeds 20,000? We go to this sampling distribution of means, we find 20,000, we say, okay, what's the probability of that happening? Well, we use z-scores or normal CDF, and you can actually approximate this, but it's 0.0228. There's only about a 2% chance that any sum of 9 days, when divided by 9 to get you a mean average, would have a mean as high as 20,000, because your means should be balancing out closer to the 18,000 mark. So, what we find is if we have a random variable that's distributed normally with a mean of mu and a standard deviation of sigma, then the probability distribution we get for x is just 1 score at a time. But if we take a random sampling of a bunch of scores coming from this distribution and want to know how the means of the samples will be distributed, that's going to be the same mean as the x itself, but the standard deviation is going to be reduced. The bigger and bigger the sample size, the less and less fluctuation that you would expect. And these are called sampling distributions of means. They're theoretically what should happen if we took millions and millions of samples of size n and we looked at how those puppies would be distributed. So again, the idea, this is 1 score at a time right here. And if you take a sample, you expect scores to be spread out. But when you add up those scores and divide by n, those sample means are going to tend to be really narrowly distributed. So every score in a sampling distribution is the mean of a sample coming out of this. So this one sample of however many scores you have when you take that one mean average would fall somewhere over there. So a sampling distribution of means describes theoretically how much fluctuation and with what parameters should we expect to see those means fluctuate. Alright, so we can see that for our fireworks thing, the red is the original distribution, and the sample means and the sampling distribution of sample means would be the green right there. Alright, last problem. Let's go back to the tree thing. Let's talk about taking a simple random sample of 7 days and then finding the probability that the sample means will be at most 9,000. Now remember, from probability, I've said right from the start that the sample size really is important. How many things are we selecting? Once you take samples of at least 5, we're probably looking at sample means or later sample proportions. So it is sample means, so we say, aha, I know what's happening. We're going to take 7 days at random from here. We don't know how those 7 days will be distributed. But when we add them up and divide by 7, we're going to tend to get mean averages that are really close to the overall mean of 10,000. So the sampling distribution of means should be much more concise than the 1 day at a time original distribution here. So we're talking about finding the mean of 7 days of tree sales, and those means should be distributed normally with an overall mean of 10,000, just like the population. But the standard deviation now is going to be 2,000 divided by radical 7, the square root of 7. This is going to be $755, I looked at it earlier, $93. So you can see that our means for any 7 days randomly added together and divided by 7, those things are going to be distributed this way. So the standard deviation falls from 2,000 a day per one tree revenue sale, but down to 755 for how much swing we should expect with means of size 7. So once again we say, okay, let's go here. We know that the sample means are distributed normally. 10,000 is our mean. We're talking about having at most 9,000. And we're no longer using that standard deviation because that's for one score at a time. We're using these parameters, so we go normal CDF, put all this information in here, and we get 0.0929. So what that means is, if you randomly selected any 7 days and found the mean average, then only about 9% of the time would you get a mean average way down at $9,000 a day or less. The next time you sample, you probably get a mean up closer to 10,000 or above. But this is an initial idea of how sampling distributions of means work, how we change. Don't forget to always change the standard deviation down to this, and then it's the same old thing. You're using a normal distribution to find probabilities.